composition of these tire particles. So we had this micro X-ray fluorescence, micro XRF, that we used, and we tried to make this work. However, our biggest challenge was again that there's so many particles in these samples. So we were going to focus on environmental samples where you had a lot of particles. So, for example, tunnel samples. So using these single particle procedures were still a big challenge to us. And also the signal that we got from our micro X-ray wasn't really strong enough to really detect the ratios in small particles. So we're hoping in the future that we can make this happen, because we're going to work with synchrotron, and this could really improve the identification process, and also trying to couple both FTIR and the XRF with synchrotron. We're hoping that that might solve a little bit of the problem with the low detection. And then we went on to the next approach, which would be then to look at the masses. That was what we did. We wanted to have a mass-based approach. So we tried out using ICP-MS, looking at different elements. We did not go for the organic components in this phase, but we went for pyrolysis GCMS. So that's what we invested in and decided to use. Yeah, so what we found was that, let's see if I mixed up my slides. No, sorry, it is a bit late and I've been up for a very long time, so I might be talking a bit strange sometimes. I apologize for that, but I hope you're all following me anyway. Yeah, so we expected there to be a very low concentration of tire particles compared to other road particles in some of our samples. So we decided to try density separation, and we followed the density separation described in papers of Klockner. He has different papers, but we followed some of these and tried to do a density separation. And then following that, we will do a pyrolysis GCMS analysis. And I'll just show you a little bit what we did. So this is an example for snow. So we have roadside snow that we melted in the lab. We took out small subsamples of this and freeze-dried it so we can get the particles. As you can see in the first picture, there's a lot of particles in this snow. And then we've added these, we've weighed and added dried material to our analysis, or to the density separation, and we use the sodium polytungstate SPT to get the density to about 1.8, 1.9. And we had some tried to make these weird things in the lab so that we can capture the fraction that will float and not mix up everything that's in the bottom. And then we did a filtration of the floating part in the end. And then we redid this 3 times to get as much as possible out of it. However, and then we expected that the tire wear particles, or that most of them should be in the light fraction, or the fraction that will float, using this density separation. And then we expected that the road wear particles, the heavy particles, would be in the bottom of this. However, when we did our analysis, we also checked the bottom part, because we wanted to figure out if we've lost something, or like how much tire particles are left in the bottom. But to our surprise, we found the highest mass of SBR, or styrene butadiene rubber from tires, in the bottom part of this density separation. And this was happening in most of our samples, and we were trying to figure out what's going on. We lost faith in density separation for a while there. And what we figured out was, that, well, first there's a large range of the densities of tire particles, which makes density separation quite difficult, because it could be that we also chose the wrong density for this. However, it shouldn't really be the main problem here. Then we looked a little bit more into what else could be happening, and we found that all these areas where we took our snow samples were areas where you had this polymer modified bitumen in the road asphalt. And since we found out that this road asphalt, the rubber that they add, the SBS rubber, when we analyzed that separately and compared it to the SBR rubber from tires, it was actually giving us the identical pyrolysis products. So it was not possible to differentiate between the SBS and the SBR rubber in the analysis that we did. So we figured out that that was mainly the reason why we had these weird data coming out of this study. So this is sort of the basis of what we've done in my PhD. Like, we had this discovery, we're trying to use some methods that were already out there, and it didn't work for us. So we had to try to figure out what we can do, what's happening. And of course, this could also be a very specific problem, because not every country has this type of SBS rubber added to their bitumen. But I think, according to literature, we're not the only country using it, so it might be that someone else also have to consider this. Yeah, so we had this rubber containing SBS. We then wanted to try to figure out what can we do with this. So we analyzed SBR rubber and SBS rubber separately, and we also analyzed it in a mixture. And we scanned this for possible unique markers. We did not find any unique markers when we did this, but we did find that the peak height, the intensity of the different pyrolysis products or markers, they varied between SBR and SBS. So what we managed to do was to have this, we can build this model where we can see that there is a distinct difference between the signals coming from SBR and SBS, and also when you have them in a mixture. So when we have the pure rubbers, this separation worked very nice. See here. And also when we had environmental samples, we also got some that were identified as mixtures, which fit with our explanation, because these were all collected from some areas where you had both tire rubbers and the polymer modified bitumen present. So they should come up as mixtures. However, when we try to look at or use this method on tires, so we have build up this library of different unused tires that are most that are relevant for Norwegian roads. When we looked at those, they had a completely different signal, which made then this model maybe not well. It didn't work for us, to be honest. So when we looked a little bit more into this, we found that these tires that we have, they had a very high complexity. There was a lot of differences between them and between the different types of tires. Like, we have summer tires, winter tires, studded, non-studded, different truck tires. And they all had very, very large variations. And some of this is due to different ratios of styrene to butadiene and the different types of SBR rubbers that they have, and also the isomers of butadiene. We also described some of these challenges in a paper together with some colleagues from the University of Queensland, Quays. So if you're interested in looking into what we described, you can read the paper there. Yeah, so this idea of trying to find a unique marker, that was abandoned. Then the second idea of trying to separate between SBR and SBS by this model, that was also abandoned. So then our next goal was to try to find markers that would have the least variation between SBR and SBS, so that we can analyze them together, so that we would not get by the pyrolysis, we wouldn't get how much SBR and how much SBS were in the sample. We would get them in a mixture. So how much of the total mixture is there? That was our last attempt here to find a method that would work for us. And we validated this with unused or these new tires that we had with environmental samples. These are the markers that we chose. We have benzene, alpha-methylstyrene, ethylstyrene, and the butadiene trimer. And we also use internal standards. And from this, we tested our markers, those markers I've just mentioned, and also are called our multiple markers. We tested the performance with these markers compared to using the 4-vinyl cyclohexane, which is presented as the marker in several other studies, including the ISO studies. And also compare them to the markers SB and SBB, which has also been tried by different studies. And we found that the markers that we chose gave a lower standard deviation in our reference tires compared to the other methods. So at least for the Norwegian tires, this method seemed to be giving us a better result. So we went with this one. Then the challenge was, as I said, now we don't have how much SBR is in there or how much SBS is in there. We have a mixture. So we had to find a way to separate between them, because the end point here, or at least the people we're reporting to, which is the road agency, they want to know how much is there from tires and how much is there from other sources. So they want to know the end point, the end source here. But that demanded some calculations. So we use traffic data, and we use the reference tires, and we calculate how much should come from each of these sources. And we also use a Monte Carlo simulation to try to predict the concentration, because the concentration of rubbers in tires, in our reference tires, are also quite variable. So we have to use some kind of simulation to adjust for how much summer tires should be here, how much winter tires, truck tires, all of these. We can adjust for that in our calculations. We also do similar things with how we calculate for road wear. We have described this method in this paper here. It came out earlier this year. Yeah. We also used we built on this method that we presented in that paper, and we added on this simulation where we can also calculate how much tire and road wear particles were in a sample, so the TRWP. And this is, I would say that this is under development, because there's not a lot of studies so far that's reporting these ratios between road wear particles and tire wear particles in the mixture. So far there's not that much data that we can build our simulations on. However, as people will start reporting more data and we know more about differences between different types of roads, for example, if you're in an urban road or highway road, these mineral encrustment ratios should be different. So when we get more data, we're hoping that this type of calculations could also be improved. But we've described how we did this in this paper about tunnels that I've added here. All right, so the next step was then to use this method. So as I said, initially I didn't expect to do a lot of method development or to go into the analytics like this when I started this PhD, but we ended up there, and then we had not that much time to actually look into the environmental samples. But we managed to do 2 studies. So we have the roadside snow, which I've already mentioned a little bit, and we had a tunnel where we looked at everything from the tunnel surface and to the release of tunnel wash water. So I'll talk a little bit about those 2 studies also here. Yeah. So for the roadside snow, we had a hypothesis, which were that the higher levels of tire wear and road wear particles were deposited close to the roadsides. This is based on previous studies done both on road pollution in general, but also a few of those that's been done on tire wear particles already. We also hypothesized that the traffic density, or the annual daily average daily traffic, was the most important traffic variable here, driving these concentrations. So we found, we confirmed our hypothesis that we found that there was a declining mass concentrations when we looked at distance from the road. So we looked at samples in between 0 and 1 meter, 1 meter and 2 meters, and then 3 meters and 4 meters from the road. And you can see some of the concentrations. And then we did an analysis trying to figure out which of these different types of variables could explain the variation, because we found a very high or large variation between different sites. So we looked at speed limit, we looked at the percentage of personal vehicles versus heavy vehicles, we looked at traffic loads, we defined areas that had this stop-go kind of thing, so it could be roundabouts or these light crossings or other types of areas where people will accelerate and brake a lot. We also included the percentage of studded tires, and we looked at distance and a few other things. And doing this, we found that speed limit actually had, or were the most important variable here, which was a bit surprising to us, because usually in these road pollution studies that we've looked at, it's the traffic load that is the most important variable. To see that traffic load is still quite important here, and also distance from the road, which was not surprising. But yeah, that the speed limit had a higher impact here than traffic load was a bit surprising to us, but interesting. And then a little bit about the tunnel study. Here our hypothesis was that road tunnels represent the local hotspots. So in Norway, we have a lot of road tunnels. We have over 1,100 road tunnels along the state and county roads. And all of these tunnels are washed regularly. And the tunnel wash water is very highly polluted. So we know this from a lot of other studies that we looked at different types of pollutants, but not looked at tire wear particles or microplastics. And we wanted in this study to look at tunnels because it's defined, at least in Norway, it's defined as a pollution hotspot, and it's an area where you can look at these pollutants without too much disturbance, because you won't have the impact of rain, and you won't have particles going up to the atmosphere, except for in the entrance. And yeah, so it's a very good place to do a study and also have a look at these highly polluted areas. So we collected samples from the road surface. That's the first one. Yeah. In this picture, you see where we took our samples. So we took them in the entrance, in the middle of the tunnel, and then in the outlet. And we took all of these dots that I've shown here. We used something called a wet dust sampler, which is sort of like a high pressurized water collector. So you shoot high pressured water into the surface, and then you collect that water sample in a bottle after. So this one works very well, especially with fine, very small particles. And we found that the highest concentrations were closest to the sidewall, so in the bank area, and also the highest concentrations on the surface was in the outlet of the tunnel. And this was a little bit surprising because in many of the other studies that we've had in Norway looking at road pollution on the surface, we found that the inlet is the area where you have most of this of the pollutants and most of the particles, like the total particle load. And the concentrations we found here were also a little bit higher than what have been reported previously for tunnel dust, looking at tire particles. And then we also included the gillipots, or the sedimentation traps, in the tunnel. And here we found the opposite compared to the road surface. Here we found that the inlet area where the highest concentrations were, and lowest in the outlet. And also the concentrations we found in the sediment here were comparable to levels previously reported for sedimentation basins. So treatment basins for runoff areas. And then the last part was to look at tunnel wash water. So this water that is washed through the tunnel will go to the drainage system, and for most of the tunnels in Norway, this water will actually just go straight into the nearest stream, or to a fjord, or any other recipient. But in Oslo, they've decided that all the tunnels here, because we have a lot of traffic, and also the environmental agencies here are a little bit more, how do I say this? They're a little bit more and really want to stop the pollution. So here all the tunnels have treatments. So this tunnel that we studied was here in Oslo. So this one has a sedimentation treatment, and it also has a rain garden after sedimentation treatment. So we've sampled before and after the sedimentation treatment in this study. So what we could see was that the untreated tunnel wash water was actually comparable to previous studies that has looked at road runoff, which was a bit surprising to us, because we had expected maybe that we would find a lot higher concentrations in the untreated tunnel wash water. We also found that it was, as you can see in this graph here, that it's quite it's lower than what we found in the snow study. So that was also a bit surprising that we had so high concentrations in this roadside snow. That was also a lot higher than what we found in this tunnel. And this tunnel isn't a low traffic tunnel either. I didn't mention that, but it's compared to at least Oslo standards, it's one of the high trafficated tunnels. We also found that this sedimentation treatment that they have for this tunnel removed 63% of the rubber particles present, which also was a bit lower than what we thought. And that's based on previous studies on road pollution, where you have this expectation that if it's something that's particle related, you would expect there to be a high removal with sedimentation. So maybe 80% isn't very strange to expect. So we are going to work a little bit more on this tunnel now in new projects to figure out what's happening and why we don't have as high removal as we thought we would have. But even though it's lower compared to the snow samples, we still agreed that road tunnels are a local hotspot, and it could have a big difference in the release of tire wear particles and road wear particles, especially if you don't have any treatment. Yeah, so a little bit conclusions. I think I'm maybe on the time. So for in this PhD or project, we have worked a lot with the analytical method. So we found that the methods improved by using multiple pyrolysis markers for the styrene butadiene rubbers. so including the SBR and SBS in this. We also found that using relevant reference tires when you calculate the tire wear particles is very important, and it gave us a better results compared to using a standard percentage. We also found that it's possible to use relevant levels of mineral content, but we need more data for this to be a little bit better. We found that tire and rubber particles are deposited close to the roads, and that the main variable contributing to particle emissions is the traffic speed, but also the annual daily traffic, average daily traffic is also quite important. We found high levels of tire and rubber particles in roadside snow, and we found that the tunnels could be a local hotspot. Last slide I think I have is a little bit about the future research needs. And I guess this is also things that most of you probably thought about already, but we are still working on the data, and there's a lot of study that's now out about tire wear particles, and there's a lot of things going on which is very nice to see. But I still think we have a way to go. We need to have more to look at the particle variation a little bit more. We need to look at aging, different particle sizes, how that impacts our analytical side of things, and also how this is actually going on in the environment. I think we also need to consider when we're doing new projects or we're applying for new projects to consider what type of roads should we include, because not only looking at the roads with high traffic volumes might not give us all the answers. So we need to include different types of roads, urban roads, country roads. We need to consider areas where we can really get some variation, so we have better data, I believe. We also, I think it's important to consider and to discuss this thing about comparable data, but also locally adapted methods. So especially for us, we saw that using relevant tires and tires that are used in Norway was a good idea for us, and it changed what type of markers seem to be better suited. And we also found that this part with the polymer modified bitumen and the SBS was quite important for our analytical side. So I think it's important to also do something that is comparable between countries and areas. So we need to figure out how to deal with that, but we also need to do something that is relevant for the areas where we're taking samples. So I think sometimes if we only try to do something that will be comparable between the whole world, then we might lose something that is relevant for the small stream where we're releasing this and we want to know what's happening. So sometimes it's important to think about these both of these aspects, I think. Yeah, and also different types of treatment. So I now also think it's important that we include studies that can figure out what type of treatments are most useful, because especially here we are getting a lot of interest from the road agency and the environmental agency. They want to have solutions. So they want us to figure out, okay, well, we know there's a lot of tire particles and microplastics out there, but we want to know which solution is the best one. So our new projects are now more focused on testing different types of solutions and figuring out what we can, if we can learn something from that. So I think it's also important to consider. Yeah. Right. So thank you for listening in.
Yeah, thank you so much for your presentation. Really interesting to hear about this from a different perspective, from the Norwegian perspective. I see clapping, so round of applause for getting through it. And I know it's late there, so thank you again for joining us at a later hour. But the few questions in the chat that I guess I'll start with, and then folks in the group feel free to to pose questions as well. I know that the majority of this group does either has or is currently doing research on tire wear. So I'm sure there are lots of questions. But the first question came from Dave, and you sort of got at this and talked about the challenges of differentiating between the tire particles coming from the tires and those coming from the road because they were chemically very similar. And I think you said there was like a difference in the peak hike. But he's asking, um, that says the tire industry tells us that particles emitted from tires are 50% tire and 50% road wear, and that he's suspicious of this. And can you give us guidance about your estimates of those proportions?
Yeah, I mean, for in our studies, I mean, we looked at we have 31 tires in our database, and as I said, there's a wide range here in the rubber content. So we have all from I think about 15%, something like that. I don't remember the numbers in my head right now, but around 15% of SBR in the mass percentage, and up to close to 60, I think, if I remember correctly. And that's for the SBR rubbers that we have. So I think just using a 50%, it's if you don't have if you don't know what you're having, if you don't know a lot about the tires used in your area, maybe using these standard percentages is fine. But if it's possible to get some data or get some tires that's most used in your area or your country, I think it's very useful to do this. So the way we're doing is that if we collect a sample during winter, so the snow samples, then I only calculate these based on the winter tires that's used. So I don't put in summer tire data into that calculations. So I think it's useful to do this if you have the data and if you have traffic data that you can apply, because you will then get more locally adapted concentrations. And I think, yeah, if you only use these big percentages or the fixed percentages, there's a big chance that you will over or underestimate the problem,
Right.
and especially maybe over, actually. So,
Right. So there's a lot of local variability too, or depending.
yeah.
Yeah. It looks like Paul, you have your hand up. Did you want to go ahead and ask your question?
I do. Hi, thanks. Great presentation. Really appreciate it. So you were saying that traffic speed has a great influence on the particle concentration, and I assume that means where the traffic is moving faster, that you have more particles. Is that true?
Yeah.
Yeah.
I didn't
And
say
so
that. Yes.
so what? Yeah. So is it just the rotational momentum of the tires just flinging particles off, or do you know what the mechanism is? Do you have any suspicion?
Well, yeah, we didn't really study all the mechanistic differences here.
Yeah.
So, and this is also based on the what's it called, the signed the speed limits. So we didn't have data for the actual speed limit, which I of course think is a bit higher usually than the speed limits. But I think there's a lot of things going on here, and what we've trying. So yeah, we found that speed limit had a very big impact on the variation, but it only accounted for 20% of the variation, which means that there's a lot of other things also going on here. And it could be that those areas where you had the higher speeds also have other there's other things with those roads that impact it as well. So it's not only the speed, and we might not be able to find all of these, like name all of these factors yet. So I think, yeah, the roads that have the really high speeds, they are typically the highways. So they're longer. So that was a little bit surprising actually, because we would maybe expect that the lower speeds, where you have a lot of stop and go, like the urban areas, would have a higher concentrations. Yeah. So,
So
the short answer is I don't really know why yet, but maybe if I come back in some time, I can shed some light on that.
So do you have any reference for the relationship? Like if the speed is 80 kilometers an hour, do you get twice as many particles as when the speed is 40 kilometers per hour? Like a linear
That we don't,
relationship, or is it?
I don't think we have enough data to say that yet. Like what type of like,
yeah.
because that's we've been, since we published this, we've been getting a lot of questions from people's that want us to give a number so that they can ask the road authorities to put speed limits down, but we don't really have that data yet.
Yeah.
So I'm just saying that there's a link here, and we want to try to explore what this has to say for the concentrations, and if there's something, if reducing the speed is something we can do, then that might also be a very good thing. In Norway we do that in wintertime. We have a lot of roads that have it's called environmental speed limit, so they reduce it from 80 to 60 due to the air quality part, which I think then also has a very good effect on other particles. So
yeah, fascinating. Thanks, very interesting.
I sort of had the same question as Paul. What's sort of the threshold for how fast we should be going to generate under a certain number of particles? But totally understand we don't know that yet.
Oh, sorry.
I'm also feeling guilty about having a bit of a lead foot and probably driving too fast. But let's see, lots of other questions. I'm gonna skip forward from mine. Here we go. Stacy asked, says, perhaps I missed this, but what was the lower limit for the size of particles that were collected across methods? So how small were you able to go?
So yeah, we used I think both studies where we had water samples. So that means the road surface samples that were collected in a water sample, and the tunnel wash water, and also the snow. All of these were filtered on glass fiber filters in the end. So the pore size were 1.6 micrometer. So theoretically, that's my lower limit. But yeah, you guys probably know how it is with pore sizes and sizes. But yeah, that's the theoretical lower limit of my samples. Yeah.
Makes sense. And I was curious about the wet-dry collection method. Do you have a link to that device or like an image of it?
Yeah. Yes, I do. We also, I think we put a picture of it in the paper as well, probably in the supplementary. But it's a device that was designed, created at the Swedish. What's the English name for that? This the Road Research Institute of Sweden. I think they were the one who designed it first, and now we have one in Norway, and the road authorities are the ones who own it and use it. And I think there's one in maybe Iceland or Finland. So it's still not a lot of these out there, but it's very useful, and it's been used a lot for different types of fine particle studies, both in tunnels and road surfaces. It's yeah. But I can send you something if you're interested to see what it looks like.
Yeah, that would be great actually. And I was going to ask this too, but George King asked if it was possible to get a list of the publications. Like if you have links that you could post in the chat. I'm sure everyone would love to read more about your results. And then here, especially on the west coast of the US, there's a lot of concern about effects of tire leachate on salmon. In some species, their lethality has been observed from levels that are potentially detectable or found in the environment. So with someone asking if there's been any research on potential effects on Norwegian salmon, or is there, are people thinking of following up to look at that?
Yeah. Yeah, I know there's at least a few smaller projects where they're going to test the Atlantic salmon that we have. Right, I mean, my institute has not started on any on salmon yet. But so what we're focused on is trying to see if we can measure this in our snow samples and in the tunnel samples. So we've done that already, but we haven't used it for a publication yet. But we did find quite high concentrations and also above this LC50 threshold that they published at least in Tian's study. So far we know that these are also present, and then we're hoping that we can use this to figure out a bit more. But yeah, we haven't had a big salmon death that we can trace back to a big issue yet. So hopefully that's because it's not a problem and not a matter of time. But yeah, we'll
That's
see.
good news. So
But there are some people working on it. Yeah.
Okay, awesome. Are there any questions from San Diego State or SFEI? I know you're all very deep into the tire particle research these days. No worries if not. It's a little bit later in the day on the West Coast. So, yeah, I guess something that we've been talking about it a lot in our group that's thinking about tire particles is this difference in water treatment, often depending on the age of the cities, like combined sewer systems versus systems that are separate, have a separate process for stormwater, and that stormwater is just running off into waterways rather than being treated. It sounds like Norway has a combination of both. Like Oslo
Yeah, I mean,
treats the sediment traps, but the other places don't.
yeah, I think well, in the cities and the bigger areas like urban areas, we do have sedimentation traps. I think a lot of the water will go through sedimentation traps, but we still have the combined sewer systems in a lot of the cities. So here it's still a big problem, like especially here in Oslo, our capital, which then has the most traffic in urban area. We do see that a lot of pollution is going straight into the fjord that we have here, and a lot of that is happening because of the overflow in the sewers. So we think that a lot of tire particles and other pollution from the roads will get there. We also find it in the treatment of the sewers, the wastewater treatment facilities that we have. So we also know that it's going in there, but it's mainly for the tunnels that we've been getting the treatment up. So yeah, we have treatment for roads outside of tunnels, but that's less common. So I think it's more now focused on the highly polluted areas, which the tunnels, which is quite important to consider. Yeah.
Absolutely. And that's something that's really interesting to think about. And I hadn't thought about tunnels being hotspots, but that totally makes sense. Of course.
Yeah. I'm just not sure how many tunnels you have in US. I haven't checked, but I guess some areas probably have a lot of tunnels. So you have mountains there as well.
Yeah, some areas do. And I mean, if you're thinking about the West Coast, we have the Rockies here, so, and other smaller mountain ranges. So, yeah, quite a few tunnels.
They probably also wash them. You have to do that unless you ruin all the equipment and the lights and everything in the tunnels. So they probably wash them as well. That would be interesting to see if there's any studies on that. Yeah.
Not that I know of, but yeah, that would be really interesting.
Yeah.
Add it to the list.
Yeah.
Great. Well, we're coming up on time. I don't think there are any other questions. If I missed any in the chat, let me know. I just see thank you for a wonderful, informative presentation. No worries, Kelly. The COVID booster completely did me in too, so I completely understand. I thought I was okay, and then I had to get someone to drive me home from work. Isn't that so? You feel better soon. But so far, I've been here at a conference for 4 days, and so far, so good. So maybe it's helping.
Hopefully, yeah.
They make us test every morning, which I think is great.
Yeah. Okay.
All right. Well, have a great evening, and thank you again for joining us at an unusual time. Great presentation, great work. Good luck.
Thank you for having me.
Yeah, good luck with your new position at NIVA.
Thank you.
And,
Yeah,
Sure. I'm sure
yeah.
we'll be seeing you again. And I think there's a session on tire particles at the conference at 8:30 then.
Okay, yeah.
We'll
I'll
be-
have to check it on Twitter and see if there's something interesting I'm missing out on. Yeah. All right.
Good.
All right.
Thank you. Thanks everyone. Good to
Bye.
see you.
Bye.